Let's take a look at lesson 0.1.5, the fuel calorimetry. So what I've got right here are two trials from burning ethanol underneath a can with water in it, as well as two trials from burning isopropanol underneath a pop can with water. We took the mass of the fuel, I guess it's called an alcohol burner, before we set it on fire and after, so that we knew how many grams we burned in each trial. And we also measured the initial and final temperature of the water, as well as the mass of the water. So we used 100 grams for our experiments here. So before we start getting into our calculations, there's a question here. It says, if it takes 4.2 joules of energy to increase the temperature of 1 gram of water by 1 degrees Celsius. By the way, that 4.2 number is called the specific heat capacity. Sometimes you'll see it represented with a capital letter C. So what if you're trying to figure out how much energy it takes to increase the temperature of 50 grams of water by 10 degrees Celsius? Well, it takes 4.2 joules to heat up 1 gram, 1 degrees Celsius, but in this situation, we're heating up 50 grams by 10 degrees Celsius. So notice too that the units cancel out, grams over grams, degrees Celsius over degrees Celsius. We're going to have an answer here, 2,100 joules. That's how much energy it takes to heat up 50 grams of water 10 degrees Celsius. This is basically what we're doing in our experiment. We're figuring out how much energy was transferred to 100 grams of water. And based on how much the energy changed, or how much the temperature changed, we can figure out how much energy that took, that fuel released, I should say. All right, so if I'm rewriting number 4's numbers in words, I'm going to say that the total energy is equal to the specific heat, that's that 4.2 specific heat, the 4.2 joules per gram degrees Celsius, multiplied by the mass, multiplied by the change in temperature. And then if we skip down to number 7, it says, what if we put that equation into, make it a little easier on the eye, and change the words to letters? So energy is actually the quantity of energy, so they use a Q. Specific heat is, we mentioned, represented with a capital C. Mass is easy, a lowercase m. And change is a triangle, delta, and T for temperature. So now we can use this equation to figure out how much energy our fuels released to the water. So this lesson kind of steps us through how to do that calculation. Now, ultimately, our final goal is not to have how many joules our fuel released to the water. It's going to be how many kilojoules were released per gram that burned off. So we need to use this equation first, but then we need to do a little more work. So again, it's Q equals the specific heat times the mass times the change in temperature. So for trial 1, I'm going to go back and take a look at my data. So for my data, the mass was 100 for trial 1, and the temperature went up from 23 to 69. That is 46 degrees Celsius. And the mass that burned off during that time, in my calculator, I'm going to do 198.7 minus 197.07. That comes out to be 1.6 grams. Oops, 1.63 grams, right? Sorry, my calculator is old. All right, So what we could do is, and it might make it easier for you, is to go through and actually calculate all of the differences on here so that when we come back, we can just have these as an easy reference. So I'm going to do 197.07 minus 195.32. So for trial 2, we burned 1.75 grams of fuel, and the temperature changed by 44 degrees Celsius. And in the burning of isopropanol, the first one is 175.3 minus 174.03. That's 1.27 grams that burned off. And then 174.01 minus 172.58. So again, you'll be doing this for all of your data. I get 1.43. The temperature here went from 24 to 66. That's a temperature change of 42 degrees Celsius. And here it went up an extra degree, 43 degrees Celsius. Okay, so for my trial 1 data right now, I need to know the 46 degrees Celsius for a mass of 100 grams of water. So for my calculation here, I want to do Q equals the specific heat for water, which is 4.2 joules per gram degrees Celsius, times the mass of my water, which was 100, times the temperature change, which was 46 degrees Celsius for ethanol for trial number 1. So when I punch that into my calculator, I get 19,320 joules. That's how much energy the fuel gave to the water. For step 2, it says I need to convert joules into kilojoules, and I do that by dividing by 1,000. So I'm going to divide by 1,000. I get 19.32 kilojoules. Now step 3 says figure out how much mass the fuel lost when it was burning. So I'm going to go back up to my data table and look at what I calculated for trial 1. The mass went down by 1.63 grams. Okay, so I'm just going to write that in since I already calculated that. So step 4, my final calculation for trial 1, is to do what answer I got in step 2, the kilojoules, divided by how many grams burned off, so that I've got how many kilojoules per gram were given off. So I'm punching this into my calculator, and I get 11.85, it's good to round to 2 decimals, kilojoules per gram. So at the bottom of this page, it actually has the data table for me to record all of this. So trial 1 for ethanol, 19.32 kilojoules were released when 1.63 grams of ethanol were used up, so the energy content is 11.85 kilojoules per gram. So now we go back and we do the same thing again, but for trial 2. So this time the temperature went up 44 degrees Celsius. So I go back here to my step 1. Oops. For trial 2, it was 4.2 joules per gram degrees Celsius, still 100 grams, and it only went up by 44 degrees Celsius. So this one is going to be a little bit of a smaller number here. Punching it into my calculator, hopefully giving you time as you're doing this with your numbers so that we can be slow together. 18,480 joules. So I'm going to need to divide that by 1,000 here. 18,480 divided by 1,000 is 18.48 kilojoules. I'm just going to write that I divided it by 1,000. Show my work there. Okay, Then trial 2, I burned off 1.75 grams of fuel. And so I'm going to do 18.48 kilojoules divided by 1.75. Answer, 10.73 kilojoules per gram were released in trial 2. So now I can record all of this in my trial 2 down here. 18.48, 1.75, 10.73 kilojoules per gram. So then I'm going to figure out my average for ethanol. So I'm going to take 11.85 plus 10.73, divide it by 2. My average is 11.29 kilojoules per gram. So now I just need to repeat this for isopropanol. And so for isopropanol, I'm going to go back up and use my little space here. For trial 1, let's see. Oops, went a little bit too far. Trial 1, the temperature changed by 42 degrees Celsius. Oops, sorry. Come on, computer. It's coming back. Okay. I'll write this all down so I don't have to keep scrolling back and forth here. Alright, computers. So for trial 1 for isopropanol, it went up 42 degrees Celsius. The mass changed 1.27. And for trial 2, 43 degrees Celsius, the mass changed by 1.43. Okay, so to fill in my table for isopropanol, I just need a little place to have some chicken scratch. Since I didn't really use my average space up here, I can do that. So I'm going to do Q equals 4.2 times 100 times the first temperature change was 42 degrees Celsius. So that ends up being 17,640 joules. Divided by 1,000 is 17.64 kilojoules. And the mass used was 1.27. So now I can just do 17.64 divided by 1.27. And I get 13.89. And for my second trial for this one, I want to do 4.2 times 100 times the temperature change was 43. 4.2 times 100 times 43 is 18,060. Oops, can't write. Okay, 18,060. Trying to erase it. So this would be 18.06, and that's for 1.43 grams burned off. So 18.06 divided by 1.43, 12.63. So now I'm going to find my average. 12.63 plus 13.89 divided by 2. My average for isopropanol is higher. 13.26. All right. So now I'm going to write a conclusion using my data. So first, answer the question. And the question was, which fuel gives off more energy per gram? So I'm going to say isopropanol releases, I'm going to spell it right. Oh, okay. My computer's not working quite right. Alright. Work for me. I'll just write over this. Okay, there we go. Isopropanol releases more energy per gram when burned. Then I state my evidence. Isopropanol released 13.26 kilojoules per gram on average, while ethanol only released 11.29 kilojoules per gram on average. And then explanation of how the data supports my claim here. So I'm going to say for this that this data supports my claim because isopropanol transferred more thermal energy to a can of water per gram burned than ethanol. So I'm giving my explanation a little bit further there, that we were measuring the transfer of thermal energy to water in this lab to explain my reasons. Number 2, how confident are you in your results? So there's a few ways that you could think about this. You could make sure that when you compare with other groups that they were also getting that the isopropanol was releasing more energy per gram. You could base it on the fact that, you know, your group's procedure ran pretty smoothly. So whatever you want to say there, I'm going to say I'm confident in my data because both ethanol trials resulted in less energy released per gram than isopropanol. A random error that I saw when I was doing this was the wicks were sometimes different widths. It was hard to keep things at a consistent height. Wicks weren't consistent. So this could lead to error because maybe you would accidentally have the wick for ethanol a little bit closer than the wick for isopropanol. And a systematic error that occurred was that some energy escaped to the air, the surrounding air, and to the can. So hopefully that helps you out a little bit with wrapping up this lab.